So our senior design project was the autonomous fire extinguisher. Our team consisted of myself, Quinn Nye, I'm an electrical engineer, Moaz Abugabel, he's a computer engineer, Alex Leonard, who's a mechanical engineer, and Ishard Muhammad, who's also a mechanical engineer. Our supervisor was Dr. Janet Dong. The problem that we are seeing is that half of all fire deaths occur between 10 p.m. and 6 a.m. when everyone's asleep. Candle fires alone cause 15,000 house fires and 150 deaths and over $260 million in damage each year. These fires start out very small and then grow to something that is too large for people to deal with, and often people are not notified overnight that they are happening, and it takes the fire departments, once they are called, 4 minutes and 12 seconds to arrive to a house. So the current market outside of what everyone has to have, like smoke alarms and detectors and carbon monoxide detectors, you could look into buying a home sprinkler system. But the problem with these is they're very expensive and they're not really fit for all types of homes. Older homes can't have these, and people who rent homes can't have these installed, and people who have apartments can't have these installed. And the other problem is that they can destroy property once they are set off and the water gets sprayed everywhere. So our solution is to make a robot that can patrol the home and detect these fires and extinguish them in a more safe way. So what it would do is patrol the main home of the house, searching for fires. When a fire is detected, it will tell the user wherever they are, and if the fire grows at all, it will begin putting it out. And the user has some input here where if it doesn't grow, I mean, it could be something like a candle, so they wouldn't really want that exterminated, they just want to know that it's still lit. So it'll wait for the user to respond, and they'll have the option to tell you what to put it out or not. So this is a motor chart of all of our parts and things that we need for this project. The sensors, the microcontroller, the fire extinguisher, the battery, how we want to actually squeeze the fire extinguisher, different materials, and how we actually want to navigate and move the robot. So we went with infrared over the LiDAR and the ultrasonic sensors because they're very affordable and cheap. They're only like $2 or $3 for an infrared. They're quick and easy for us to implement on our microcontroller. So they're really fast in real time, and they sense up to 2 feet, which is well within the range that we would need to detect objects while our robot is moving around. They're small, so they don't take up a lot of space inside the enclosure, and they're also unaffected by natural light and temperatures, and this is important why we didn't pick ultrasonic sensors, because they actually variable their sensing range and how far they sense with heat. So if there's a fire present, they wouldn't actually be able to tell that it's there. And we didn't go with the LiDAR because we thought it was a little more than we needed, and the LiDAR is over $100. So we picked the Pi over going with an Arduino for a couple of reasons. One, it already has onboard Wi-Fi, which is something that we would need. It has onboard Bluetooth. It has I2C, which will interface with our thermal camera that we need to use. It's written in Python, which we know, and it also has its own camera that isn't thermal, so we can take a picture with that, which we'll talk about later. So we opted to go with mixed housing materials over strictly plastic or strictly aluminum or steel, because we need flexibility in this. We need to put in support in the aluminum base where we need it, and aluminum in itself is pretty lightweight and strong. And then we can use the plastic to create like a cover over it to make it more aesthetically pleasing and cover up all the electronics. So we, after doing our battery calculations, we would like to go with always roaming, but we got it up to a pretty realistic time of 10 hours of actual roaming around. So our robot can roam for 10 hours, but and then it'll have to go to charge. So it'll still be useful for when you're away for 8 hours or when people are sleeping. But then after that, it'll have to go back. So we chose to use the 10-pound fire extinguisher just because we want to make sure the robot has as much extinguisher possible for it to use over having a smaller one, because we didn't really think weight was a concern of ours. We could buy bigger motors that would be able to move the robot around. And we chose to orient it vertically because we had to. How a fire extinguisher actually works is there's a hose that goes down to the bottom of the extinguisher, or of the tank. So when it's pulled, it goes up the straw and sprays out the hose. So that's why we had to orient it vertically. If we did horizontally, we don't ever get to use half the extinguisher. So for the squeezing mechanism, we opted to go with using a linear actuator because for our motors, we're going to have a motor driver board on there, and we found a linear actuator that would work, and it only requires 12 volts, which is perfect because those are the motors we have, so we have an extra terminal where we can use that for. We could have also used a pneumatic air cylinder, but then we'd also have to have air running out to our fire extinguisher, and having that wouldn't be very convenient as opposed to just using linear actuator.
This is our pairwise comparison table. We compared 5 different things, being affordable, easy to use, safe, reliable, or efficient. And out of these 5 things, we chose that safety is the #1 thing for our project. This is the white box flowchart, which is the brain and how the robot thinks and functions. So it starts in the beginning charging, and after the battery is fully charged, it will go to the first room, see if there's fire, no, go to the next room. If the battery at that point needs to be recharged, then it will go back, otherwise it will keep checking for fire. And once it checks for fire and finds one, it will trigger the buzzer, the alarm, and then it will approach the fire, take a picture, and send it to the user, and then wait for a feedback. Unless the user does not respond back and the fire grows, then it will exterminate the fire by itself. Otherwise, it will wait for the user till it gets feedback. And then after it's done with all of that, it will go back to the dock to recharge. This is a black box diagram. For us, it's simple. We have the docking station and the robot having the battery, the regular camera, the motors, the IR sensors, and the Raspberry Pi as the main controller of the whole system. Here's another circuit diagram that shows how the components are hooked up and connected to the microcontroller for this project. So we have a couple of IR sensors, as Gwen have mentioned, and flame sensor, thermal camera, the buzzer, and we are also using a joystick to manually move and control the robot in case the person doesn't want to lift it or it's heavy for them or something like that. They can use the joystick to manually move the buzzer back to its docking station or wherever they want to move it to. We also have some little stuff like a LED to show if it's working or not working, like that, and switch if they want to turn it off or not. These are the user tests we were planning on using with the robot, and they're simple, just like hard on, see it starts roaming when it should be, does it avoid obstacles or hit to them, does it travel at safe speed, does it dock when it needs to be recharged, or just does it just die, and does it flip over, does it support the weight of the fire extinguisher on top of it or no. And the last thing we wanted to test in here was to see if fire comes up, would the product actually put it down or not. This is our objective tree, which uses the 5 characteristics from the pairwise diagram we showed before, and we showed that safety is the most important thing for us. So we want to make sure that it's traveling at a slow speed, a safe speed, and it avoids obstacles, and the design does not have sharp edges and is not exposed to many mechanical parts. This is an overview of our Gantt chart that we were following till stuff started falling apart because of the pandemic. Here's a bill of the materials for the electrical side of the design, showing the thermal camera, the quantity of the IR sensors we're going to use, the buzzers and all that stuff, and the total price as well down there. There are some problems that we might face, being the thermal camera would lose vision due to the extinguisher. So when the gas gets out of the fire extinguisher, it might block the thermal camera, so it might not see the fire in front of it correctly. So we were gonna use a technique where it would spray, stop and see, spray, stop and see, like that's a second or two delay between each spray when it sprays till it like sees everything again and makes sure that the fire is extinguished. And also COVID-19 slowed us a lot because we cannot need to put the mechanical side and the electrical side together, and we were not able to do the testing, which is something we were looking forward to do. And as far as the robot being not able to see, that's why we chose to add some flame sensors on it, because flame sensors detect fire in like a small range, and they would work better if there are fumes, while the thermal camera might completely lose vision. Things we wanted to test when we built this is the vision system, making sure that the thermal camera is actually picking up the temperatures correctly, is identifying out objects, and the regular camera being able to capture pictures and send it via MMS to the user. And the second and most important thing is the extinguishing system, being sure that the robot can actually extinguish the fire and put it out. The third thing we wanted to test is the autonomous roaming, making sure that the robot does not hit objects and it avoids it, and it can go back to its docking station as well. And we want to make sure that the app is communicating correctly with the robot, that it's sending the layout of the floor correctly, and it's setting out the periodic time roaming time as well. For the future, we want to continue building the robot when hopefully the labs open again, so the mechanical people can cut the metal and put it together, and then we can integrate the electrical part with it and assemble the robot. And once that's done, we're going to go and debug it and make sure it's functioning and standing up to our requirements and specifications as we need them. Here are a couple of references that we used in this presentation. And this is a last slide that's open for questions, and since we are not actually doing the presentation in person, if you have any questions, you can reach us at our emails, me or Quen, with any questions you guys